Hello there, Mr. Sutton here with the BC Calculus 8-4 Extra Practice Number 4 Solutions on Vector Free Response Practice. On this calculator-based free response problem, we have a particle moving in the xy plane on the times between 0 and pi, which is going to be important in a moment, and that's given by this x and y of t set of parametric equations. Our first task is just to sketch the path of the particle in the xy plane on this coordinate system here, and then indicate the direction of motion along the path. So they're going to want some arrows. So to do this, we're going to have to go into the parametric mode in our calculator. So to do that, we're going to go to Mode, and then down here where it says Func, we're going to arrow over to Pair and press Enter. Now we're in parametric mode. So we go to y equals, and we notice it's no longer y equals. Now it's x1, y1. So this is where you put in your two parametric equations. For x, we've got this craziness, and for y, this 3 sine of t. I'm going to do those off camera. So I changed my mind. I did the x one off camera, but I'll do the y one on camera for you, just so you can see how I'm getting the t here. So let's see here. We've got 3 sine, and then to get t, you just have to actually press the x button. It's x, t, theta, or n, depending on which graphing mode you're in. So t, and then close that parentheses. So now we also have to get the right window for this. So for the window on this one, if you go to Window, you'll notice that we're no longer doing necessarily x and y, max and min, although you could. There's also this t min and t max. So we want to go from 0 to pi. So let me put in pi here. There we go. And this is what we're going to go with. Let me just do zoom 0, zoom fit, and see how this works out. And if you want to adjust the x and the y window, you actually can. So let me do, let's see here, x min, it looks like they went out to -4. X max was +4. And y min, they went down to -2. Just if you want to duplicate what they have, I mean, it's not going to hurt anything. Let's do graph now. Okay, so there we are. And let me just graph that one more time. And actually, I want to see the direction that these things are going. So just to keep track of that, what you can do is if you go to the, not the equals, if you arrow actually back a little bit further to this line here and press Enter, you'll see there's different styles. I'm going to do this this style here that looks like a little line going into a 0. So that's going to show me the direction things are going, the order it happens in. So check it out. There we go. Now we have this little bouncing ball showing us the order that we're going in. So when I graph this out, it looks like we're starting in the origin and then coming around this way. So I'm going to draw some arrows that just indicate that direction. And then I'm done. For this part of the problem, we want to know on what time between 0 and pi does the x of t parametric equation attain its minimum value, and then what's the actual position at that time. So we need both an x and a y there. All right, well, to figure this out, since we have this interval, this closed interval here, one way you could do this is with the candidates test. And, I mean, that's going to depend on whether or not there's more than one critical value. So why don't we go and find some critical values? If there's more than one, we'll use the candidates test. If not, then maybe we don't need the candidates test. So we need to take a look at x prime of t and see where that equals 0. Well, in order to figure that out, I have to take the derivative. I actually have to show what the derivative looks like before I'm allowed to solve an equation with the calculator. So using the power rule, this is going to be, let's see, 2 times 1/2 cancels, so you just have a t. And then for this stuff, we're just going to have 1 over 1 plus t. And we want to know where this is either going to be 0 or undefined. Now, we don't really have to worry about undefined because the only place that's going to happen is at -1, and we're not worried about negative time because, well, t is not allowed to have any negative time. We have to stay between 0 and pi. So I'm going to go ahead and graph this on the calculator and solve it. So here's my calculator, and this was that parametric graph that I did in part A. I'm going to clear this out, and I'm actually going to go back to mode, and I'm just going to go back into func mode here because I'm not really comfortable with that parametric mode. Let me go to y equals now, clear out whatever's in there, and I'm going to enter my x prime function here. So we've got x minus, and then I'll do fancy fraction 1 over. We've got 1 plus x. And I want to see where this attains a value of 0. Now, since I'm graphing this with respect to t, I'm just going to use this interval from 0 to pi. So let me go to Window, and we'll do 0 to pi for the x min and x max. And keep in mind that x in this case really refers to t. It's just the input value for this particular function that we're going to graph out. So let me do zoom 0. Here's what we're looking at. And it looks like there's just one critical value right here. So let's find what that critical value is. Do second trace, and then option 2 for 0. Let me move my spider a little bit to the left of that, and press enter. Move a little bit to the right, press enter again, press enter one more time for good measure. It's about 0.6180, some change. So I'm going to give that a name. I'm going to call that value there that I just found, I'm going to call that P. So P is approximately that number that I just found. And I'm actually going to go back on my calculator, and I'm really going to store that. So let me quit out of there, and then let me press the store button to store the x value I just found. We'll store that as alpha p, or whatever letter you want. Doesn't really matter, but we're going to use it again, because if this ends up being the time at which we attain the minimum value, we're going to want to be able to plug this back in to the x and the y of the original there. Okay, so now let's go ahead and analyze this a little bit more. So we notice, actually, just taking a look at this, that x prime is negative from 0 to p. And x prime is also positive from p to pi. Well, what does that mean? It means that x itself is decreasing until we get to this spot, and it's increasing after. That means that this has to be the absolute minimum value on the interval. Another way of thinking about it is there's only one critical value, and it's a relative min, so it's also going to end up being the absolute min. So we know then that our absolute min for x of t happens at time p. So given that, we just have to find the point at time p, which is to say we need to find x of p, comma, y of p. So that gives us more to do on the calculator. Let's go ahead and take care of that. To make this a little bit more streamlined, I've actually entered x of t into my y2 and y of t into my y3. Maybe I'll need them later on, who knows. So let me quit out of there, and I'll just do alpha trace y2, and let me plug p into that. So parentheses alpha p, and then close that and press enter. We get about negative 0.290. And then let me go back and do the same thing. I'll just yank my input from before. And this time around, I'm going to do, instead of y2, I'm going to do alpha trace y3. And press enter. 1.738. For this last part of the problem, we have a bunch of questions. At what time between 0 and pi is the particle on the y-axis? And then once you figure that out, we want the speed and acceleration vector at that time. So to figure out when you're on the y-axis, well, that's going to happen when you have an x value of 0. So we basically need to figure out, when does this x of t function they gave us equal 0? And that's a question that we can answer with the calculator. So I'm back in my y equals for this, and you'll notice that the x of t function, which was t squared over 2 minus ln of 1 plus t, I put that in my y2 because I needed it for part b, but now I need it again. I want to graph this out and figure out where this y2 function hits the x-axis. So let me go and deselect y1 and also y3. I don't want to graph those. I'm just going to graph this one. And for my window, let me just make sure, yep, I'm still going between 0 and pi for the input, so that's good. Let's zoom fit this thing. And I have to do zoom fit again, even though I did it before, because this is a different function now. So it's going to have different y values on the same interval. So we see that there's really one spot here on this interval where we're hitting the x-axis if you don't count this time in the beginning. So let's see what that time is there. Do second trace zeros, and then let's see, let's go a little bit to the left of that. I think I'm to the left. Press enter, and let's press enter a little bit to the right. Press enter one more time. So that's about 1.2859. and I'm going to name that number q, just so I can refer to that more easily. So let me go back, and I will immediately store that on my calculator. So store, we'll go alpha q, or whatever letter you want. Okay. So that's the time that I'm going to be using to find the max speed and accelerate, or find just the speed and the acceleration. Now, in order to get the speed and acceleration, I'm going to need the first derivative of x and y. And I'm going to need the second derivative for acceleration, but let me start with one derivative here. So we already found in part B that x prime was this right here, t minus 1 over 1 plus t. We need to find y prime as well, and that's actually not so bad. That's just going to be 3 cosine of t. So that could be worse, but I need to explicitly write out what x prime and y prime are for what I'm about to do next. So let's do the speed first. To find the speed, you need to take the square root of the sum of the squares of the derivatives at whatever time is in question. So basically, we need square root of x prime of q squared plus y prime of q squared. This setup right here. And since I actually didn't need to define x prime and y prime in order to just take their derivatives on the calculator, but this makes it a little bit easier to do in the calculator if I already know what these functions look like. So I'm going to go and enter these functions into my calculator. I've actually already got x prime entered as y1, so I guess I'll put y prime in y4, and then I'll go from there. So here we are back in the y equals. As promised, in y4 I've put my y prime here. So let me quit out of there now, and I'll just do all of this on the calculator. So I'll do the square root of, and now we need to do x prime. That was alpha trace y1 is where I stored that. X prime of q, so alpha q, and now I'm going to just square that, and I'll add that to, let's see, y prime of q squared, so alpha trace y4 is where I put y prime, and we'll do alpha q in there, square that, press enter, hope for the best, and we end up with 1.196. Doesn't look like they had any units here, so we don't have to give them any units. We also need the acceleration vector, though. So the velocity vector was x prime of q comma y prime of q. For acceleration, we need x double prime of q, y double prime of q. Now the good news is, since I've already defined what x prime and y prime are, I can actually just take their derivatives directly on the calculator at a specific spot. And this is really why I needed to define x prime and y prime. I didn't really need to define them for speed in order to get credit writing this, but I do need to have them defined if I'm going to take yet another derivative at an individual point. So let me go in the calculator and work this magic. We'll start with x double prime of q. So I basically need to take the derivative of x prime at q. So I'll do math 8. That brings up my derivative. I'm doing dx. And in here, I want x prime's derivative, so I'm going to do alpha trace y1. And I want to do this at q, so in this little x box here, I'm going to put alpha q. Press enter. It's about 1.191. There we go. And let me do the same thing for y. So the good news is I can just yank my input from before. And instead of using y1 in there, I'm going to do alpha trace and do y4, because that's where I stored y prime. So now this is giving me y double prime of q. Press enter. Negative 2.879. And that should just about do it. For this free response, no calculator free response, we have a particle moving around with an x and y parametric function given as follows down here. For our first task, we want to find the velocity vector in terms of t, and also the speed at time 0. So these work together here. We're going to need the velocity vector to get the speed anyway, especially since we're not allowed to use a calculator on this. So let me get the velocity vector. I'm going to take the derivatives of x and y individually with respect to time. So for x prime, we've got, let's see, 2e to the 3t times a tail of 3, so that's actually going to be 6e to the 3t. Little chain rule going on there. And some more chain rule on this next one. This is going to be negative 7e to the negative 7t. So that's x prime. For y prime, more of the same with these chain rules. This is going to be 9e to the 3t. And now we have a minus minus, so this is going to be plus 2e to the negative 2t. So for the velocity vector, we actually have to write it out as a vector. I'm just going to write brackets x prime of t, comma y prime of t. I mean, we've already defined what x prime and y prime are, so there you go. Okay, so for the next thing, we need the speed at time 0. So our general setup for this, we're going to have to take the square root of x prime of 0 squared plus y prime of 0 squared. Now, looking at x and y prime, this looks a little bit intimidating at first. I mean, you have to plug it in here, you got to square it, you got to add it, square root. There's a lot going on, but let's take it one step at a time. X prime of 0, what's that going to be? Well, the nice thing is when you plug 0 in for t, it just gives you an exponent of 0 in all these e factors. E to the 0 is just 1. So really, you just have to take the coefficients and combine those for both of these. So this is really just going to be 6 minus 7, which is negative 1. So that's what we're squaring for that first term. And y prime of 0, well, this just ends up being 9 plus 2, which is 11. So we're squaring 11 and adding that. And you've got all constants at this point, so you could leave it like this. Or if you want to call it the square root of 122, that's also an option. Either way. For this part of the problem, they want us to find dy over dx in terms of t, and then find the limit of dy over dx as t approaches infinity. So recall from part A, x prime was this expression here, and here was y prime of t as well. And that's important because dy over dx, when you're talking parametrics, is really just y prime of t over x prime of t. Now, since I've actually defined x prime and y prime, I could write this and get credit for this part of the problem. They said define dy over dx in terms of t, and I've done that. I mean, if you want to know what y prime is, there it is, look it up. But I am going to rewrite these because I'm going to write them a little bit differently to make my next step a little easier. So I'm going to write y prime here. I'm going to write this as 9e to the 3t plus 2 over e to the negative or e to the positive 2t, like so. And I'll write x prime as 6e to the 3t minus 7 over e to the 7t. The reason I'm writing it like that is it's going to make it easier to take the limit as t approaches infinity of dy over dx. As t approaches infinity, these bottom-heavy fractions here are going to go to 0. So my numerator then is just going to end up being 9e to the 3t because, again, this second term here is just going to 0 as your denominator grows infinitely compared to the numerator. Down here, this other fraction is also going away because it's bottom-heavy. So that's just 6e to the 3t. And writing it like this, it's pretty easy to simplify. Just cancel out those e to the 3t's. And if you want, you can reduce the 9 over 6 to 3 over 2. And there we are. For this part, they want to find each t value at which the line tangent to the path of the particle is horizontal, or explain why none exists. So none is an option on this one. So if I want to know where the tangent line is horizontal, I'm basically looking for places where y prime, the up-down motion of the particle, is 0, and at the same time x prime, the left-right motion of the particle, is not 0. These two things need to be true at the same time for us to have a horizontal tangent line. Okay, so let's start by figuring out places where y prime is 0. So here's my y prime again, 9e to the 3t plus 2e to the negative 2t. I want to find a t value such that this y prime comes out to 0. But there's just one issue, and you can see this even without a calculator. These are both exponential functions. Exponential functions, if they have a positive coefficient, are always going to be positive. They have that horizontal asymptote going on in one direction or another. They never touch the x-axis. So because y prime of t is guaranteed to be positive in this situation, it can't be 0, which means there is nowhere you're going to have a horizontal tangent line. For the last part of this problem, they want us to find each t value where the tangent line to the path of the particle is vertical, or explain why none exists. So pretty much the vertical equivalent of what we did in part C, trying to figure out where things were horizontal. Now, if you want to know where your particle has a vertical tangent line, you're basically asking where is x prime, the left-right motion, 0, and at the same time y prime, the up-down motion, is not 0. So let's start by figuring out where x prime, which was this function again that we found in part A, let's see where this equals a value of 0. So one quick way to solve this equation is to just multiply everything by this denominator down here, e to the 7t. If I do that, this becomes 6e to the 10t. We're adding the exponents there. This term is going to be just minus 7 as the denominator cancels out. And we're just going to still have 0 on the other side. So let's see here. Adding 7 and dividing by 6, we have 7 over 6. To get rid of this e, I'm going to take the ln of both sides. So we have ln of 7 over 6 equals 10t. And then we'll have t equals ln of 7 over 6, all of that divided by 10. So I can write 1/10 or all divided by 10, same thing. So this isn't quite enough to justify the existence of a vertical tangent line. It's close. We said that x prime had to be 0, and y prime, we have to talk about y prime not being 0. Because if y prime is also 0 at the same time, that would tell us that the particle was basically standing still rather than moving up. The good news is, in part C, we established that y prime cannot equal 0 because it's made up entirely of exponential functions. Well, what that means is that we do indeed have a vertical tangent line at this t value here. And just to clarify what I just said about y prime not being 0 because it had entirely exponential functions, it had all positive exponential functions. Note here that we got away with having all exponentials because one of them was a negative value, so we were still able to make this equal 0, whereas we could not do that with y prime. Anyway, there's the location of your vertical tangent line. For this calculator-based free response, we have an object moving in the xy plane with x of t comma y of t as the position vector, and we didn't actually get the position functions here, but they did give us the derivatives of those two functions, dx over dt and dy over dt. And we're also told at time 0 we are at the position -3 comma -4. So our first task is to find the speed of the object at time 4. So basically for speed we need to take the square root of the sum of the derivatives at time 4. So that's going to be square root of x prime of 4 squared plus y prime of 4 squared. Now the good news is they already gave us the functions x prime and y prime. That's these two functions right here. So we can just plug this whole thing now into the calculator. So to save myself a lot of trouble down the road, I'm actually going to enter dx over dt as my y1 in my calculator. And for y2, that's where I'm storing my dy over dt. I know I'm going to need them again later, and I certainly need them now. So now let me quit out of there. And to do this efficiently, I'm just going to do square root. And now to do x prime of 4 squared, I'm going to do alpha trace y1, because that's where I stored x prime. I'm going to plug 4 into that, so parentheses 4. And then I'll put a little square out there, because I'm squaring that. Now let me do plus alpha trace y2, because that's where I stored y prime. Plug 4 into that as well, and square it. And then just press enter for this whole thing. And that's 2.912. They didn't give any units, so they don't get any units. For this part of the problem, we want the total distance traveled by this object over the interval from 0 to 4. So for this, we're just basically going to need the integral of speed from time 0 to time 4. So integral from 0 to 4 of square root of, and now we just need general stuff, so x prime of t squared plus y prime of t squared. Again, all that's in a square root. And I have a dt for my differential as well here. So a few details to be careful about. Now, because I already have x prime of t and y prime of t defined, I can just put them in here like this without copying everything in there. So let me do all this on the calculator now. Now here's my setup on the calculator. I have the integral from 0 to 4, just like I have on the paper here. And square root of x prime was really y1 in my calculator. Y prime was y2, so I'm just squaring those. And then notice that I have an x instead of a t, but I defined all these functions in terms of x anyway. So as long as you use the same variable consistently, my x is going to do in the calculator what my t is doing on the slide here. So pressing enter for the answer, we get a total distance of 6.423. On this part, they want us to find x of 4. So for this, we're going to use the fundamental theorem. We don't have a formula for x of t, but we can get any value of x that we want if we start with the initial value of x, which is -3 in this case, and then just add the integral from 0, because that's the time that this x value existed, from 0 to whatever input we want for time. So in this case, we need the integral from 0 to 4, so we're adding that. And then in here, I need the rate of change of x, so x prime of t dt, which we've already got defined up here. And the rest is just up to the calculator. So plugging all that into the calculator, I've got -3, integral from 0 to 4, and x prime, that's what I stored in my y1, so that's what I'm putting in there. Press enter, and we get the x value of -0.892. For this last part of the problem, they're going to make us do a little more work on this than they did on the first 3 parts. So for time t greater than 0, positive times, they're telling us there's a point on the curve where the tangent line to the curve has a slope of 2. Okay, we'll take their word for it. We want to know at what time t is the object at this point. So basically find the t where dy over dx equals 2. And then whatever time that is, we need to plug that in to an acceleration vector. Well, first we need to write an expression for dy over dx, because we don't have that yet. So in general, with parametrics, dy over dx is going to be your dy over dt over your dx over dt. So basically y prime of t over x prime of t. And this counts as an expression for dy over dx because we've already defined, or they already defined, y prime and x prime. It's equivalent to the things we have up here. So we just need to figure out on the calculator where this equals 2. Once I've written this out, I can just plug this into the calculator and now solve for time. To solve this on the calculator, I'm going to go into my y equals here, and in y3 I'm going to create a new function, basically this dy over dx function. So I'm going to need a fraction, so let me do alpha y equals n over d form, and then I need y prime, well that's alpha trace y2, and then I need that to be over x prime, so alpha trace y1. So there it is. I'm going to need to graph this out and see where this equals 2. So let me put 2 down here so I have something for it to intersect with. And one other thing, let me just deselect these other functions because I don't want to graph them. Now what window should I graph this on? Well, I'm not really sure. Did they give us any kind of window? Not really. They said time greater than 0. That's kind of vague. So we'll just make up something and hope for the best. They said that there is a point on the curve where this is true. They didn't say times, so presumably if we find one, we can assume it's the only one. So let me just go to window, and I'll start at 0 for x min, and for x max, oh, I don't know. Let's go with 10 and just see what happens. All right, zoom fit. And I can certainly adjust the window if I need to, but we've got to start somewhere. So this is my dy over dx, and it's a little slow to graph because it's really a quotient of 2 other functions. And hey, there's that line, y equals 2, or whatever equals 2. So we do have an intersection there. Let me do second trace intersect and move my spider a little bit closer and press enter 1, 2, 3 times to get the point 1.358 and some change there. So that's the time that this happens at. And I'm going to give that time a special name. So I'm going to call that time P. And again, that's approximately equal to this 1.3577 number if you round it off. And I'm going to go on my calculator, and I'm also going to actually store that as P, or whatever letter you want. So let me go to stow. That's going to immediately take the intersection x value and put it in whatever letter I want. So let me do alpha p for that, because I'm going to have to actually plug this into my acceleration vector later on. So it'd be helpful if I can just call that back whenever I need to. Let's talk about acceleration. So acceleration, this is velocity right here, x prime and y prime. acceleration is x double prime and y double prime. Specifically, if I want the acceleration vector at this point, I'm looking for x double prime of p, comma, y double prime of p. So that's what my goal is. Now the question is, can I just do this on the calculator without showing you what x double prime looks like algebraically, and the same thing for y double prime? And the answer is yes. I've already got x prime and y prime defined right here. You are allowed to just take the derivative of a function like these at a single point without showing what the derivative looks like algebraically. So I can just do this on the calculator without showing any other work. So let me go and do that now. So here's what I'm going to do back on the calculator. Let me do math 8 to pull up derivative. We're going to do dx, and I'm going to take the derivative of x prime to get x double prime. So that means I need to do alpha trace y1, because that's where I stored x prime. And for the x value that I'm evaluating this at, I'm going to use this point p. So alpha p, press enter, and we get about 0.135, which I'll put down there. Now let me do the same thing for y double prime of p. Now the good news is I can just yank my input from right here, and the only thing I need to change from what I did earlier, I need to take the derivative of y prime instead of x prime. So instead of y1, I'm going to do alpha trace and replace that with y2. Still doing this at p though, so press enter, and that's 0.955.